Okay, let's look at this scenario. We have an unpolarized light beam starting in air, and it's hitting a different medium that has a refractive index of 1.73. The light is hitting this medium specifically at something called Brewster's angle. The question asks us what happens next, specifically about the polarization and angles of the reflected and transmitted light. We have four options to consider. Alright, let's break this down starting with understanding what Brewster's angle actually is. Think about light hitting a surface. Normally, both the reflected and the light that goes through the transmitted light are at least partially polarized. But there's this one special angle of incidence. When unpolarized light hits an interface at this specific angle, the light that bounces off, the reflected light, becomes completely polarized. This very special angle is what we call Brewster's angle, often denoted as theta b. And here's a cool property of this angle at Brewster's angle. The reflected ray and the ray that passes into the new medium, the refracted ray, are actually perpendicular to each other. They form a 90-degree angle. So how do we find this Brewster's angle? Well, there's a straightforward formula for that. Brewster's angle theta b is related to the refractive indices of the two materials. The formula tells us that the tangent of theta b is equal to the ratio of the refractive index of the second medium, n2, divided by the refractive index of the first medium, n1. In our problem, the light starts in air, so the refractive index of the first medium, n1, is 1. The light is hitting a medium with a refractive index of 1.73, so n2 is 1.73. Plugging these values into the formula, we get the tangent of theta b equals 1.73 divided by 1, which is just 1.73. Now we need to figure out which angle has a tangent of approximately 1.73. If you check your trigonometric values, you will find that the tangent of 60 degrees is approximately 1.732. So based on this, Brewster's angle theta b is approximately 60 degrees. Now that we know Brewster's angle, let's figure out the angle of reflection and the polarization state of the reflected light. First, the angle of reflection. This is pretty simple thanks to the law of reflection, which states that the angle of incidence is always equal to the angle of reflection. In this case, the angle of incidence is Brewster's angle, which we just found to be approximately 60 degrees. Therefore, the angle of reflection is also approximately 60 degrees. Next, the polarization of the reflected light. This comes directly from the definition of Brewster's angle itself. Remember, at Brewster's angle, the reflected light is by definition completely polarized. Okay, we've dealt with the reflected light. What about the light that passes into the medium, the transmitted light? We need to calculate its angle, called the angle of refraction, theta r. To find the angle of refraction, we use Snell's law. This law relates the angles and refractive indices of the two media. We plug in our known values, n1 for air, n2 for the medium, and our angle of incidence, theta b, which is about 60 degrees. Using Snell's law with these values, we solve for the sine of theta r. This calculation gives us a value very close to 0.5 for the sine of theta r. The angle whose sine is 0.5 is 30 degrees. Therefore, the angle of refraction theta r is 30 degrees. Let's talk about the polarization of the transmitted light and check that special relationship at Brewster's angle. The transmitted light is always partially polarized. It doesn't become completely polarized like the reflected light does at Brewster's angle. This is an important distinction. Now remember, we said that at Brewster's angle, the reflected ray and the transmitted ray are perpendicular. Let's check if our calculated angles hold up. The angle of incidence and thus reflection is approximately 60 degrees and the angle of refraction is 30 degrees. If we add the angle of reflection and the angle of refraction, we get 60 degrees plus 30 degrees, which equals 90 degrees. This confirms that the reflected and transmitted rays are indeed perpendicular at this angle of incidence, validating our calculation of Brewster's angle and the angle of refraction. Okay, let's summarize our findings. We found that at Brewster's angle, which is about 60 degrees incidence, the angle of reflection is also around 60 degrees, and the angle of refraction is about 30 degrees. Importantly, the reflected light is completely polarized, while the transmitted light is only partially polarized. Now let's evaluate the given options. Option 1 claims the transmitted light is completely polarized with an angle of refraction near 30 degrees. While the angle of refraction is correct, the transmitted light is only partially polarized, so this option is incorrect. Option 2 states the reflected light is completely polarized and the angle of reflection is close to 60 degrees. This perfectly matches our findings, so option 2 is correct. Option 3 says the reflected light is partially polarized and the angle of reflection is near 30 degrees. This is incorrect because the reflected light is completely polarized and the angle of reflection is about 60 degrees. Finally, option 4 claims both reflected and transmitted light are perfectly polarized with angles of reflection and refraction near 60 and 30 degrees. This is also incorrect as only the reflected light is completely polarized. Based on our analysis, the findings align with option 2. The reflected light is completely polarized with an angle of reflection around 60 degrees, matching the Brewster's angle. The transmitted light is partially polarized with a refraction angle around 30 degrees.